So, climate change is a hugely complex issue because the Earth is really complex and has all sorts of different uh, systems in it and is extremely large. But we can use the first law to simplify it and use some of our knowledge about heat transfer to simplify it and understand why climate change is a real and important phenomenon. All right. So that's the basics of the first law. I want to take us a little bit to explain how we can use that to think about climate science. It's a sort of interesting thermodynamic problem, in part because we have a system that is so completely isolated, right? So we take our Earth system and we isolate our system. We know this is our first law of thermodynamics. The change of energy equals uh, the thermal energy into the system minus the work done by the system. Um, but on the Earth system, because it's essentially a vacuum around the Earth, there's no work. Okay, so there's no work on the space surrounding it when it's actually not pushing anything, um, and it's not changing volume. So we can get rid of our work term, and we end up with a change of energy as Q in minus Q out. Now, we talked about heat transfer, and we know that conduction and convection require a medium, right? They need some kind of matter to transmit energy. Well, we're surrounded by a vacuum, so there's no conduction and there's no convection from the Earth to space. So the only kind of heat transfer we need to worry about is radiation. And so we can say the change in energy of the Earth's system is the incoming thermal radiation minus the outgoing thermal radiation. Yeah, it's a pretty simple thermodynamic system. It's actually insanely complex, but we'll call it simple in these terms. So then, how do we estimate those radiation terms? Let's go back to our heat transfer, right? And we know that different materials have different rates of emission and absorption, right? We hit that epsilon term. And what we're mostly interested in here is absorption, right? So we're interested in the way that the environment absorbs radiation. So what happens on the Earth? Well, you have incoming radiation that hits the Earth, and that's coming from the sun, which is very, very hot. And the wavelength of that incoming radiation is different because of that temperature of emission. Okay. Then we have radiation coming from the Earth, which is cooler than the sun, and going back out into space. All right. So we have two different kinds of radiation that have two different wavelengths. This matters because E can actually be a function of wavelength, right? So there are going to be some materials that can absorb, say, very little light from a high temperature source, but are going to absorb more energy from a low temperature source. Okay, and we have a couple of examples of that: carbon dioxide and methane. So the high temperature radiation from the sun, carbon dioxide doesn't absorb much of that. But then when it warms the Earth and the rate tries to radiate back out from the Earth's surface, it's coming from a lower temperature, has a different wavelength, and carbon dioxide actually does absorb that. Okay. We should be happy about this, right? Because if this didn't happen, then the Earth would be much, much colder. Okay. The fact that carbon dioxide absorbs that Earth radiation means that we have what's called the greenhouse effect, right? That it basically acts as a little bit like a blanket around the Earth. It keeps some of that warmth inside. Okay, so the problem is that over the last 150 years, we've been pumping a bunch of carbon dioxide into the atmosphere, right? And you can see that in this plot here, right? They're geologic variations, right? So over the last million years, we've ranged from about 170 to 300. But you can see the sort of types of changes that happen. They happen over a long period of time. Um, this is from here to here is 50,000 years. We can see in the last 100 years, we've gone up by about 100, a little over 100. And more recently, we can see that that climb is pretty steady and in one direction. So what does that mean for the Earth system? Well, it means normally we would see a balance between the radiation in and the radiation out, so that the overall energy of the system would remain pretty similar, right? Um, so that would mean essentially that in the short term, the overall energy of the Earth is not really changing. So, is this the case anymore? Well, not really, right? So now, because we have a larger amount of carbon dioxide, our Q out radiation is getting smaller, right? So the radiation from the Earth is being absorbed by more carbon dioxide. So we have a smaller Q out rad, right? It's less than the Q in rad. And if we put that into the first law, we find that the change of energy is going to be larger than zero. That is, the amount of energy being stored in the Earth system is growing. Okay, first law tells us that the energy within the system is going to increase. And we can see that with temperature data, right? So here's temperature data over the last 100 years. You know, this is basically the beginning of the Industrial Revolution. And you can see those temperatures are climbing. And again, we can look at that over a longer period of time, over 2,000 years, and we can see some really significant changes in carbon dioxide here, and that those sort of match up with our temperature changes. So, okay, so it's not surprising that the increase in energy leads to higher temps. But more generally, it leads to higher storage of energy in the Earth system. And we know that energy can be stored in all sorts of different ways, right? We've seen you can store it chemically. It can be stored in latent heat, right, in the change from a solid to a liquid, or a liquid to a gas. And so the increase in energy has multiple effects, right? It might change, create warmer seas. It's going to release some of that latent heat or latent energy in the polar ice caps. We're going to have more energetic storms. The big picture is there's just more energy in the system, and that has significant effects on climate and the weather. Now, exactly what is that going to mean? Where is it going to get warm fastest? How are ocean currents going to be affected? When are sea levels going to rise to a certain level? That's really hard. The Earth system is stunningly complex, and even the best climate scientists have trouble trying to take into account the many, many, many variables involved. But the big point is, and that is basic thermodynamics, is that the energy in the Earth system is increasing, has been increasing, and that energy has to find a place, right? It has to be stored somewhere, or it has to change the potential or kinetic energy of our system, whether that's, you know, any of these, you know, higher temps, warmer seas, less ice caps, but we know that those things have to happen because of just some basic science. All right, so that's the end of the first lecture on thermodynamics. All right.